So in this part, we're going to generate cloning primers, which require a few different parameters and some wiggling around or noodling around on your end to add restriction sites to the ends of the primers that you generate. So back in Primer 3 Plus, you want to go to a fresh tab. We want to start a fresh primer search. So let's change the tab on the top left from generic to pick cloning primers. This changes what parameters are available in all tabs going forward. So you copy your plasmid sequence or 10 kilobases of genetic context and paste it into the template sequence box. Kind of similar, well, very similar to what you did for the detection primer search. So as before, you copy the full length of the sequence you wish to make cloning primers for. So your gene that you wish to make cloning primers for. If this is a coding sequence, copy the full length, including the start and stopped codons, unless you're doing fancier things, into your computer's clipboard. Now you want to search for that sequence in the text box using your browser search function. So in the Mac, you are using Command plus F, in Windows Control plus F. So the software will find this sequence that you are trying to make cloning primers for, but go ahead and manually re-highlight the region found by your browser and then click the included button just like we did before when we were looking for detection primers. So once again, this will tell Primer 3 the start and end of your target amplicon. Warning here, be very careful with your copying and pasting moves. Now you want to click into the General Settings tab, and we're going to change the optimal primer length to 25 and make sure that optimal primer melting temperature is set to 60 degrees Celsius. Don't change the primer length ranges unless the ranges does not contain your target sequence length. Once everything looks right, press the Pick Primers button on the top right. The primers that you generate will not be as perfect as detection primers, as you don't let Primer 3 search around. Depending on how bad the sequence start and stop is, thermodynamically speaking that is, you may need to do a nested PCR, which is more complex and beyond the scope of this tutorial. Since the primers generated are going to be the binding side sequence of the final cloning primers, it's important to make them as nice as possible. Primer 3 will throw up flags and tell you why they think the current design sucks and give you a sense of how bad. In this case, there is a hairpin in the left forward primer that is stable at 47.5 degrees Celsius. This flag just means the hairpin stability is above the default settings, and the default settings are actually user adjustable. So Sebastian is saying here he designs for a 60-degree primer melting temperature and run a PCR protocol that is melting temperature -5. So as long as that is reasonably above the hairpin temperature, he has no issues. So when in doubt, add up to 10% volume by volume DMSO to your PCR reaction to help flatten out any hairpins. What a cool tip! Copy the primers to your Plasmid Design software as you did before. Note that when you scroll down on the generated primer page, the highlighted primers are exact at the start. I imagine it should be exactly at the start and end of the included region, as expected for cloning primers. Okay, so this is where things get tricky and fully dependent on what you wish to achieve cloning wise. So let's go with a simpler example of adding 2 unique restriction sites at the 5' and 3' end of this target sequence for cloning into a different plasmid. To do this, depending on your plasmid design software, it could be an automated procedure, but in case you are lacking resources, let's do things manually. So if you're using the free version, we're going to do it manually. In this example, we wish to add the EcoR1 restriction endonuclease recognition sequence, or the cut site, to the 5' end of this, in this example, a few GFP coding sequence, and the KPN1 cut site to the 3' end. So the first step is to look up the recognition sequence for these restriction enzymes. So you can go to New England Biolab's webpage to type in EcoR1 in the search bar and select the first hit showing a product landing page for EcoR1. And in this case, it's EcoR1L, I believe. So you need to write down the 5' to 3' recognition sequence for EcoR1, which happens to be GAATTC. And now you're going to add that to the 5' end of your forward primer. Be sure you are writing it as if the primer sequence is written 5' to 3', which is default primer 3 sequence output. Again, depending on your plasmid design tool, you will notice that the primer now has some sequence floating up off the 5' end of the primer that does not match anything. This is good. It means we added a unique sequence which does not bind upstream of your primer, which will be integrated into the amplicon during PCR. That's nifty. It's okay if some of the newly added bases bind upstream, as is the case for the last C in the EcoR1 recognition sequence example. Now, simply adding the cut site recognition sequence is not enough, as we may need to add some padding upstream from the cut site to ensure that the restriction enzyme lands with plenty space or ample space for efficient cleavage. Some enzymes are quite bulky and need a few extra bases to the left and right of the recognition sequence so it can mount the DNA. We live in a material reality, and this is a cool reminder that these molecules take up space and need space. So let's refer to the incredible results NEB provided for us in this link here, so their webpage, which will tell us how many bases we need to have beyond the recognition sequence for optimal binding. So this page lists the cleavage close to the end of DNA fragments for restriction enzymes. So you scroll down or search for EcoR1, and Sebastian's saying here he buys the high fidelity version of a cutting enzyme if it's available, which may be different in padding needs to the original. So be sure to check the needs for your exact enzyme. So NEB provides this table, and in the table you see the name of the enzyme on the left and the rating of adding an extra 1, 2, 3, 4, or 5 base pairs, delineated by the plus symbol, where more pluses means more efficiency, up to a maximum rating of 3 pluses. For EcoR1, adding 4 base pairs gives it the maximum optimal padding for efficient cutting. Let's add a few base pairs to the 5' end so we can pad the EcoR1 cut site and make the enzyme happy. I like adding, so this is Sebastian, he likes adding A's and T's since they contribute less to the overall melting temperature of the primer. And if you remember, the G and C delta free energy is higher from the previous video that is on this website. So he tends to add TATA out of habit. So let's try that. Now we move to the reverse primer and repeat steps that we've just gone through. So using KPN1 as the 3' cutter that we want to add. And note here KPN1 only needs 2 bases of padding, so he just adds a TA to the 5' end of the KPN1 cut side as seen. So save both primers and congrats, you've made cloning primers. To verify, please use your Plasmid design software to simulate the PCR, or at least make sure that if those primers were to run, the resulting cut sites manifest along with the needed padding. SnapGene paid version has amazing PCR simulation tools, but this software is expensive. An alternative that Sebastian uses and he will do a tutorial on is a Plasmid editor, or you can use a personal version of Benchling. But with Benchling, he doesn't have the experience. Always check your sequences manually, and if possible, simulate the entire cloning run to make sure that any hand slip did not occur. Blast your resulting part and never stop being rigorous about your data integrity. Trust nothing. Check everything. Now you can proceed with ordering your new primers, and best of luck with your cloning adventures.
Strong.